In this video, I want to talk about shifters. So there are three types of shifters that we can build in digital logic. We can have logical shifters, arithmetic shifters, and rotators. So let's just go over each one of them one by one and see how they work. So for logical shifters, they shift the value to the left or right and fill the empty spaces with zeros. So let's just take a look at two examples. So here we have a 5-bit binary number 11001, and we want to shift it or logically shift it 2 places to the right. So that means that any bit that we have here will be shifted 2 times to the right. So the final value still has to have 5 bits. So let's just start shifting from the right. So when you shift this to the right, what happens is that it basically goes beyond the possible bits. So this bit and this one would be out of the final value. This 0 that we have, when you shift it 2 places to the right, now it is going to be the first bit in the result. Then let me just choose the blue color. We have this 1 here. You shift it 2 places to the right, now it's going to be the second bit. And then finally this one, if you shift it 2 places, now it's going to be the third bit. As you can see, we have shifted this 5-bit number, and now we only have these 3 bits left, but their location is shifted 2 places to the right. So these 2 additional spaces that now we have, or empty spaces that now we have, they're gonna be filled with zeros. A similar procedure can be applied for logical left shift as well. So we have the same 5-bit input. The output result is also going to be 5-bit. So again, I'm gonna start shifting from the right. So if I shift this 1, 2 places to the left, instead of being in the first bit, now it will be in the third bit. So this one now appears here. This 0, if it's shifted 2 places to the left, it's gonna be on the fourth bit. And this 0 bit, if it's shifted 2 places to the left, it's gonna be on the fifth bit. And now again, you see we have 2 empty places that we fill it with zeros. So this is the logical shifter. The arithmetic shifter is the same as the logical shifter, but for the right arithmetic shift, we fill the empty spaces with the old most significant bit, or generally speaking with the sign bit. So let's just see how this thing works. So I want to arithmetically shift this bit 2 places to the right. So this is the symbol for arithmetic shift, and this basically shows the amount of arithmetic shift. Similarly for the logic shift, this is the symbol for logic shifting to the right. This one is the symbol for logic shifting to the left. So the output still has 5 bits. When we want to shift a number using the arithmetic shifter to the right, we start again from the rightmost bit. So if I shift this 2 places to the right, it basically goes beyond the limit. The same is true for this 0 as well. Shifted once, it's gonna be on the first bit. Shifted twice, it's gonna be beyond the limit. For this 0, if I shift it 2 places, it was in the third bit position. Now it's going to be on the first bit position. Let's just do the same for this one. It is in the fourth position. If I arithmetically shift it to the right 2 places, it's now going to be on the second bit position. So we have 1 here. For this one, if I shift it 2 places, it is going to be on the third bit position here. So we have 2 empty places now. So in the logic shifter, what we did was that we filled these empty places with zeros. With arithmetic shifter, what we do is that we basically copy, let me just choose a different color. We basically copy the most significant bit from the original number into these places. So we have 1 here and 1 here. And because of this, the result of arithmetic shifting to the right is different than the result of logical shifting to the right, especially for the numbers that have their most significant bit to be 1. If it was 0, it would be the same, but when the most significant bit is 1, now the result of arithmetic right shift and logic right shift are different. So as you can see, if you have, let's say, a number that is signed, whether it is sign magnitude or 2's complement, and the most significant bit, for those numbers represent the sign bit. So after you right shift it, you keep the sign in the arithmetic shifter. Now let's see how it works for the left shift. And for the left shift, it is exactly the same as the logic shifter. So the final result that we get for arithmetic left shift is going to be exactly the same as the logic left shift. So this 1 is now going to be here, this 0 is here, and this 0 is here, and these 2 empty places are filled with zeros. So the arithmetic left shift and the logic left shift produce exactly the same result. The arithmetic right shift and the logic right shift result can be different, especially for the numbers that have their most significant bit as 1, or you can say negative numbers. And then the third type of shifter that we can have is a rotator, which rotates bits in a circle such that bits that were shifted off of one end are shifted into the other end. So let's just take a look here. So here we want to shift, or basically rotate, this number 11001 2 places to the right. So the output has 5 bits. So let's just start from the rightmost bit, and let me just choose the black color because the color here is black. So if I rotate this 2 places to the right, since I said these bits are practically considered to be placed in a circle, when this one goes out of the right end, it comes back from the left end. So shifting it 2 places to the right, that basically puts it in the fourth bit of the result. So we have 1 here. Then I shift 0 2 places to the right, so 1 place, and then 2 places. It's going to be the 5th bit now. This 0, when it's shifted 2 places to the right, it's going to end up at the first bit. This 1, when it is shifted 2 places to the right, it's going to end up in the second bit. And this one, when it is shifted to the right 2 places, it's going to end up in the third position. Let's just do the same for the left rotation as well. 2 places, for left rotation. So I'm gonna again start from the rightmost bit. Let me just use the black color here. So I rotate this, or I shift this 2 places to the left. So it is in the first bit now, it will be on the third bit. Then this 0 shifted 2 places to the left, so it is on the second bit now, it will be on the fourth bit. Then this 0 is shifted 2 places to the left, it was on the third bit, now it will be on the fifth bit. This 1 shifted or rotated 2 places to the left, it will be first on the fifth bit, and then if you shift it one more time or rotate it one more time, it will be on the first bit now. So it's going to be 1 here. And then finally this one, if you rotate it 2 places to the left, it's going to end up in bit 2. So as you can see, we have some differences between these types of shifts. And also pay attention that the symbol for performing rotation is ROR when you want to rotate to the right, and ROL when you want to rotate to the left. So these are the same result as we calculated. So now you might think, how can I implement such a function using the logic component that I have seen before? And the answer to that is by using multiplexers. So the general design of a shifter is something like this. So this is an example of a logical right shifter. So we have an input, let's say we have a 4-bit input from A3 to A0. So the bits are A3, A2, A1 and A0 in this number, and the output is also 4 bits. So we have Y3, Y2, Y1 and Y0. And then in addition we have the shift, or the amount of shift, which is also provided as one input. So since we have 4 bits, that means that at most we can have 4 positions of shift to the right. So that's why we use 2 bits to show the shift amount. And as for the symbol, we use the symbol for logical right shift. So the internal circuit inside this module looks something like this. We have 4 examples of 4-to-1 multiplexer. This is another 4-to-1 multiplexer, another and another. As you can see, they all receive the same shift amount input. But the way it works is that the inputs are now connected a bit differently. So let's just go over the all possible combinations and see what happens. So the shift amount can be either 0, 0, 0, 1, 1, 0, and then 1, 1, since it's only 2 bits. So when the shift amount is 0, 0, that means that the first regular input of the multiplexer is going to be selected to be delivered to the output. So that makes Y3 to be A3. Y2, the 0, 0 input is connected to A2, so Y2 is A2. Y1, the 0, 0 input is connected to A1, so Y1 becomes A1. And Y0, the 0, 0 input of this 4-to-1 multiplexer is connected to A0, so we have Y0 to be equal to A0. So this is for shift amount to be 0. So when there is no shift, as you can see, y3 equals a3, y2 equals a2, y1 equals a1, and y0 equals a0. But now let's see what happens when the shift amount is 0, 1. So that means we want to logically shift the 4-bit input one place to the right. So when the shift amount is 0, 1, for all of these multiplexers, the 0, 1 input of the multiplexer will be selected. So for this one that creates y3, the 0, 1 input is connected to the ground. So that means that y3 is going to be 0. The 0, 1 input of the second multiplexer is connected to A3. So that means that y2 is going to be A3. The 0, 1 input of this multiplexer is connected to A2. So y1 becomes A2. And finally, the 0, 1 input of the fourth multiplexer is connected to A1. So y0 becomes A1. So as you can see, with the shift amount of 1 to the right, y0 now, y3 is now 0, and the other values are also shifted. So if we have a3, a2, a1, a0 shifted one place logically to the right, the output is 0, a3, a2, and a1, and that's actually what we expect it to be. Let's just see what happens if we have the amount of shift to be 2 places to the right. So when the shift amount is 2 places to the right, that means its value is 1, 0. So the 1, 0 input of the first multiplexer is connected to the ground. So y3 is 0. The 1, 0 input of the second multiplexer is also connected to the ground. So y2 is again 0. The 1, 0 input of the third multiplexer is connected to A3. So we have A3 here. And then finally the 1, 0 input of the fourth multiplexer is connected to A2. So we have A2 here. So if we have A3, A2, A1, and A0, and we right shifted 2 places to the right using logical shifter, the output is 0, 0, A3, A2, and that is actually what we expected it to be. So based on the same analysis, when the shift amount is 1, 1, the output for y3 is 0, the output for y2 is 0, the output for y1 is 0, and finally the output for y3 is going to be A3. So if we have A3, A2, A1, and A0, and we logically shifted 3 places to the right, the final result is going to be 0, 0, 0, A3. Of course, you can have more than these possible combinations for the shift amount too, right? But let's say if the shift amount was 4, or it was 4, then your result would be all zeros, right? So it's a trivial result. It doesn't make any sense. So that's why we choose the number of bits for the shift amount, and based on that the multiplexers to be 4 to 1, right? Because beyond that it is trivial. So similarly, we can design a similar circuit to perform logical left shifter, arithmetic right and left shifter, and also right and left rotators. So I highly recommend you do that on your own. So you might ask, what is the use case of these shifters? They are very useful as being used for multiplying or divider circuits, especially if you want to multiply a number by a power of 2, or you want to divide it by a power of 2. So for this purpose, to keep the signs intact for the numbers, we usually use the arithmetic shifter circuit. So let's just take a look at some examples. So assume that these numbers that we have here are 2's complement numbers. So these numbers are 2's complement. So this one has a weight of negative 2 to the 4. This one has a weight of 2 to the 3. This one has a weight of 2 to the 2. This one 2 to the 1, and finally this one 2 to the 0. So we know that this number is actually 1 in decimal. So if I shift this, or arithmetically shift this 2 places to the left, what I get is 0 0 1 0 0, or in decimal this is 4. So the input was 1, the output is 4. So this 2 that you see here, that basically is the power of 2 that we have here. So if we arithmetically shift a number several places to the left, it looks as if we multiply that by 2 to the power of the number of shifts that you apply. So here, since we applied two left shifts, that is basically multiplying this by 4, and you can see the result here. What about this one? As I said, let's consider these numbers to be 2's complement numbers. So if you convert this from 2's complement to decimal, the value that you get is negative 3. So if you multiply this by, let's say, 4, the value that you should be negative 12. That's in fact what's happening here. We have 1 1 0 1, which is 2's complement form of negative 3. I arithmetically left shifted 2 places, and what I get is 1 0 1 0 0. So this is in fact a negative number because the sign bit is negative, and its value, when you calculate it, multiply it basically by these weights, it is going to be negative 12. Of course, you should realize that if I, let's say, shift this 3 places to the left, the result that I get is going to be 0 1 0 0 0, right, which is not a negative number. So in all cases, you should keep in mind how many times you can shift a number to the left or to the right, so the value is still meaningful. But nonetheless, generally speaking, shifting a number to the left means that we are multiplying it by a power of 2. You also need to consider that logical left shift and arithmetic left shift, they were exactly the same, right? So it doesn't matter whether you do it like this, basically logic left shift, or do it arithmetic left shift. The results are exactly the same. For the right shift to make sense, you definitely need to use the arithmetic right shift, especially since if you want to keep the sign intact. Because for the arithmetic right shift, what we had was we basically copied the most significant bit, or the sign bit, into the empty places. So let's just take a look at some examples. Here we have 0 1 0 0 0. Again, we assume that this is a 2's complement number, so this one is basically 8 in decimal form. If I arithmetically right shifted 2 places to the right, what I get is 0 0 0 1 0, which is in fact 2. So if you right shift a number by a certain number of bits, that is equivalent to dividing it by a factor of 2. And the factor is basically the number of places that you shift. So we have 8, we right shifted, or arithmetically right shifted 2 places to the right. and now we have 2. Let's just take a look at another example. This one is 1, 0, 0, 0, 0. In 2's complement form, this is equivalent to -16. So if I arithmetically right shifted 2 places to the right, that means that I am actually dividing this by 4, right? So the final result needs to be -4. So in fact, arithmetically right shifting this number would give us 1, 1, 1, 0, 0, which is in fact -4.